oversees a rich portfolio to deliver fundamental scientific discoveries and technical breakthroughs in support of U.S. DOE missions, offering a unique culture of entrepreneurship for translating science into solutions to the most critical problems facing society at the nexus of energy, environment, and security. I believe there are over 600 people in the directorate with 4 divisions and over $500 million in research funding. Before joining ORNL in 2015, he was Executive Director of the Qatar Environment and Energy Research Institute, QERI, where he led the establishment and execution of programs in renewable energy, water conservation, and atmospheric sciences. He has also held several technical and senior management positions at the Pacific Northwest National Lab, PNLL, where he was a laboratory fellow and led the computational sciences and mathematical division at PNLL from 2003 to 2013. He holds a PhD in structural mechanics from Washington State University, an MBA from the University of Washington, and is a registered professional engineer in the state of Washington, also in the state of Tennessee now. He is currently Professor of Energy Policy, Planning and Administration at the Dennison Center for Interdisciplinary Research and Graduate Education at the University of Tennessee. He is also an adjunct professor for the School of Material Science and Engineering at the Georgia Institute of Technology and has published over 250 refereed articles and holds 2 patents. So please welcome Mohammad.
Well, good morning, everyone, and thank you for the opportunity to give you an overview of Oak Ridge National Lab. I'm going to talk about one area, which is the area of additive manufacturing, and later on I'll touch on some of the large field experiments we're doing in environmental sciences, and I'll talk a little bit about something called gene to ecosystem on bioscales, and tell you a little bit about our aspiration in that area. This is Oak Ridge at glance. The lab is about the numbers you see right there in terms of research expenditure. And we have roughly about 5,000 employees at the lab. I'm going to say about 1,600 of them hold doctorate degrees, and about maybe 3,000 total are in research, and the rest are in support. We actually have lots of research guests at Oak Ridge, those who come to work in the user facilities and spend an extended period of time at the lab. That's the 3,200 research guests. But if you look at visitors, we have lots of visitors, right? Just fly-by visitors. In terms of our energy portfolio, we actually have a very diverse energy portfolio from fusion to fission. Actually, the first continuously run reactor in the world was actually at Oak Ridge National Lab, and the genesis of molten salt reactors also at Oak Ridge. So we have a very rich nuclear heritage from fusion, especially we emphasize plasma, and fission, then energy efficiency in buildings, in the transportation sector, in manufacturing, in various sectors. In the area of renewables, we tend to emphasize bioenergy, but at the same time we provide, I'm going to say, cross-cutting capabilities, enabling capabilities to various areas in renewables. Our material portfolio, when you look at the Department of Energy, and there is an office within the Department of Energy called the Office of Basic Energy Sciences, Oak Ridge tend to be the largest, really entity in terms of resources within that. And the reason is because of our heritage. Remember I said, we started in the nuclear space, so there's a lot of emphasis on structural materials, and national labs tend to morph. So over time, we have a lot of work on functional materials, and today we're working on quantum material. And I think Amit has part of that, In terms of computing, today we house the #1 machine in the world called Summit. is a 200 petaflop machine. It consists of CPUs and GPUs. The GPUs they have a tensor core in them and can do calculations at half precision, single precision, and double precision. Now, with that, you can actually run, like we run comparative genomic calculation, and that's scaled to 3.2 exaops on that machine. And again, when you have user facilities, you have to be in the business of data. We're really right here in computing. We're trying to bring data to the same level of computing. Data is really, really important, including what you do with the data in terms of the analytics and machine learning, etc. Today we have one nuclear reactor at Oak Ridge called HYPER, the high flux isotope reactor. It's a research reactor. We use it to look at materials in harsh environments. We actually use it to produce both stable and medical isotopes, and we do a lot of neutron diffraction using that reactor. We also have a spallation neutron source. It's the world's most intensive neutron source. Again, you can image materials. We are able to image living things, cells and so on. But we're in the process of starting a new journey of upgrading that to what we call the second target station, which would have 10 times the intensity and shorter wavelengths, so we can actually do more in soft materials, polymers and biological organisms. And like any entity, this is the input on the left-hand side, the output on the right-hand side, and so we try to emphasize scientific excellence in what we do, but at the same time, as a national lab, you need to go from science to actually commercial outcomes, so you have to think about innovations in terms of patents and licensing and so on. So these are some of the numbers right there. So now I'm going to zoom on manufacturing. It's one small aspect of the lab. Okay, and so we have the main campus of Oak Ridge National Lab is what you see right here. And on the main campus of Oak Ridge National Lab, we have some joint institutes with the University of Tennessee. They're actually built by the state of Tennessee on the campus of Oak Ridge National Lab. We have one in biological sciences, one in computational sciences, one in neutron sciences. There's one in material science. It's not on the campus of the lab. It's rather on the campus of the University of Tennessee. And this is what you see down there is the computational complex. We're in the process of actually acquiring an exascale machine that will be deployed in 2021. And these machines consume a lot of electricity. Yes, you have to pull a lot of electricity there, and so that's the computational complex. We have other activities outside the main campus, and they're in an area called Hardin Valley. There's three buildings. This one right here is the National Transportation Research Center. It's a DOE user facility focused on advanced transportation, from electrification to advanced combustion to mobility to cybersecurity of vehicles and things like that, including things like e-fuels, and things of that nature. This facility is what we call our grid center. It's mainly focused on electrical and electrification, so we have a battery manufacturing facility, and in the facility we're focused mainly on cobalt-free type materials and manufacturing of those, and also solid-state batteries, right, and how we make them and whatnot. And then, the business of building to grid, vehicle to grid, network microgrid, and transformers, solid-state transformers. And clearly, you have to think about sensors and on the electrical grid, but also you have to think about cybersecurity. And the marquee thing here is really trying to use fiber optics and use quantum information communication or theory and quantum encryption to encrypt the stuff. So we're trying to emphasize that, and we try to do cybersecurity of the electrical grid out of the public internet, right? And so that's the capabilities in the second building. In the third building is the manufacturing demonstration facility. We say it's demonstration. There's a lot of big machines, but nonetheless, there's a lot of really great technical work and fundamental work that happens there. And that would be the main topic that I'll talk about. So in terms of our vision for advanced manufacturing is really to focus on digital manufacturing. The future is for digital manufacturing, but to get there, you really need to integrate, focus on data analytics, artificial intelligence, and automation, along with some of the manufacturing capabilities like roll-to-roll, additive manufacturing, or if you're thinking about making composites and things of that nature. So the idea is really to enable digital manufacturing. That's what we're trying to focus on. To enable digital manufacturing, you need to think about automation, you need to think about data, and analytics associated with that. Clearly, computing is also embedded in that. Now, the manufacturing demonstration facility has core research programs, and I'll highlight the areas of the core research programs. Has a lot of industrial collaboration. And the idea, if you really want to be able to do impactful things, industry tend to have, I'm gonna say, cool challenges. Right? And if you try to address them, you're not going to just address them by applied work, like heat and beat or anything like that. You'll find that actually you have to dig deeper into science to be able to address these challenges. To deal with the industry, we normally have what we call moonshots, and I'll show some examples of moonshots. We also emphasize education. We have lots of students in the facility. We have a partnership with the University of Tennessee called Governor Chairs, and there's 16 of them. There's 3 of them in the manufacturing area. They're mainly renowned people funded in partnership between the university and the lab, and they got students, and we have the students in the manufacturing demonstration facility. Okay, so in terms of what we try to do in the facility, these are the core, what you see, the wheels are the core research area. So there's a lot of work done in physics-based simulation and advanced characterization. So a lot of modeling, I'm going to say, from fundamental models, multi-scale models, to reduced order models. That we span all of that spectrum, but also to do some of the modeling activities, you need to also collect data. And you collect data as input to these models, but also to validate these models. So I'll touch more on that as we go forward. There's a lot of work in the area of system optimization for the machines and improving performance characteristics through material processing development. And I'll also touch on that. And a big area is qualification and certification. When you do additive manufacturing, how do you know that your parts are actually free of defects? Or if you have defects, these defects will not have adverse effect on your final properties. So that's when you actually need the convergence of in situ, ex situ measurement. You generate a lot of data. You couple that with your modeling and simulation to qualify the process of how you make the parts. Okay, so that's really critical. One of the things we're doing, and I'll say more about it, we're actually trying to print a nuclear reactor. Okay, and I'll show some of that. Okay. So the NDF is the DOE only user facility focused on advanced manufacturing. It has, I'm going to say, when it comes to additive or composites, it has every machine one thinks of it. Okay, so there's large scale metal systems. So you got multi-arm robots. They deposit materials, and some of them can be actually taking material out. So this is the business of additive and subtractive. And so you have to look a lot at automation and controls of these systems. We have systems to do polymer additive manufacturing for both thermoplastics and thermosets, so you have something that deals with reactive materials. There is systems in the metal powder system, both laser or electron beam. And then the area of machining. Again, when you do additive manufacturing, it's like near net shape, but the surface finish is not really smooth. So if you actually want smoothness in your surface finish, you have to do machining, right? So in some parts, you can do machining after the fact, but if the part is fairly complicated, then you really need hybrid machines where you can print and machine. Well, when you print and machine, you can actually alter texture of these surfaces, you can alter residual stresses, you can alter deformations, so there's a lot of challenges and issues associated with that. Mentioned, the manufacturing. Again, you have to think when you buy these materials, they're in liquid form, it's like welding processes. You melt the material. So there's a lot of phase change, so you have to watch after your thermal profiles and things like this. And so the next run you do will affect the properties in the previous run. So truthfully, you need large models or models that run on large machines, and they happen to be multi-scale models. Okay? So you can invent stuff to deal with your grain evolution and things like that, or your crystal plasticity, whatnot, okay? All the way to thermal profiles and then things like that. And then we try to do metrology and characterization. You can do stuff for small parts, but you can take the whole part and do full body CT scan of it. And there's some of the statistics on the right-hand side, and that's the facility, I'm going to say 3 months ago. Today would be different. These are some of the energy generation type models. So if you look in the United States, tools and dies in the United States are not produced in the United States anymore. They left. Okay, so a lot of the tooling and everything that we buy today is really done with tools and dies. But tools and dies are done overseas. And so the question is, how do you reclaim it? Right? To make a tool, like if you take, say, one back I worked on metal forming, superplasticity of aluminum alloys, and in the Clinton administration we were focusing on lightweight automotive things in the partnership for new generation vehicle. If you look at the Cadillac Eldorado itself, the door on the Cadillac Eldorado has 14 pieces. You have to join them together. Every piece you need a male and female die. The cost of a male and female die is about $1 million. So if you want to make dies, it's fairly expensive. The lead time is fairly large. So the question is, can we use additive manufacturing to do that? And can we do all of the conformal cooling and things like this in these dies? So this is one thing. These are actually turbines, wind turbines, and so a lot of them are materials that are hard to join. How do you make it? That's actually a Navy vessel right there on the left-hand side. It's a submarine, and can you actually print these in you could print them quickly, but you could print them from bio-derived materials where you put them in some place and after some time they just vanish. Can you do that? But anyway, this is the Governor Sugar building in New York. Okay, we've actually printed molds to make the facade on the building. If you try to do stuff from normal forms, they're labor intensive, etc. It takes time, and they degrade fairly quickly. Can you make molds that actually last for a long time, give you the right dimensional quality? This is the reactor. This is just a part of the reactor. So we're printing the shell. This is the core of the reactor, and we're printing the fuel elements. Okay, and I cannot tell you what's the fuel, but we're printing the fuel elements. We encapsulate the fuel, and it's all done, in ceramic material. It's a refractory metal. It's a 3D printing. This is just kind of a propaganda material on who we work with and things like that. Okay, so there is really cross-cutting things here. So we tend to emphasize large-scale metal areas or large-scale polymers. So if you look at additive manufacturing a few years ago, you only be able to print, maybe a centimeter cube by centimeter cube in maybe a few minutes. Okay. So the question is, how can you print massive amount of materials, get the right geometry, but also the right microstructure, right? And so that's what we try to emphasize. To do that, you need to focus on the systems, you need to focus on the material, the simulation and the data analytics and the characterization. Another area is the metal powder area, and the example of the nuclear reactor that I shared with you is done in powder beds, and again, similar things. Composites and polymers, you can lay out fibers and try to infuse the polymer and the fiber using additive techniques. We'll go through the same thing. The same thing when you look at hybrid systems. So these are the materials, the simulation, the metrology, and the systems of the cross-cutting areas. Oops. So again, some of the examples that I mentioned there, you can see this. We're able to print with ceramic materials, again, aluminum series alloys for high performance automotive applications, tooling, and I'll touch on that in a bit, and refractory metals for energy and defense systems. And this is a polymer for lightweight structure. This is for actually this thing for the wing on 777 system. So it's fairly easy to try and to print a geometry, okay? But how do you control the microstructure? So this chart right here shows two different microstructures, okay? So a columnar microstructure and equiaxed microstructure. So this is the DOE logo here is done like that. So to control the microstructure, you need to control your thermal profiles, your rastering technique, when you raster, and how you raster. So it's really the combination of the modeling capabilities, the AI, your sensors, and all of that. So we're able to control the microstructure quite a lot. And actually, let me see here if I have a picture of that. I'll come back to it. So what we did is we printed the Mona Lisa, okay? And the Mona Lisa on one side, you have a columnar microstructure. On the other side, you have an equiax, it grains, okay? And that's really an extensive modeling and simulation effort, and then so on. So as I said, you can actually come in here and print a part like this, and you need, let's say, a different microstructure, different strength in this region. Clearly, properties is a function of microstructure, right? And your defects and so on. So the question is, if I need a certain property in a certain location, a tailored location, what can I do to do that? And that's something we've been really successful at doing. So we can optimize the microstructure fairly well. This is one example. As I said, we can show you the Mona Lisa as another example for that. So to be able to control the microstructure, so we have to understand, microstructure models from phase field, etc. Kind of discrete methods in terms of powder scale models, continuum scale models, finite element, and so on. Thermomechanical modeling, and then when you got all of these and you got that good understanding, what you put in your machines is really a reduced order model. So it's a response surface of some sort, right? And it can be a multi-dimensional response surface, it can be a deterministic response surface or a stochastic response surface, but that's what you really need, okay? To build the accurate response surface or a surrogate model, that's actually a lot of AI work. And I think today, if you look at AI And where people use artificial intelligence, people use artificial intelligence to build response surfaces. So the response surfaces that we build are based on models and also the data. So the models we use to fill in gaps in data, and then we got the data, right? And we establish these response surfaces, and you can put them into your machines to control the machine and so on. So then the question really becomes, I initially said, our goal is really to enable digital manufacturing, right? So if I actually can, in a facility like this, come up with these response surfaces and so on, you could imagine, for certain machines and certain parts, response surfaces are available somewhere in the cloud, like apps, and you download these things into your machine if you're somewhere in the Midwest, right? You don't have to have a PhD or anything like this to be able to do something like this. Now, with these, to be able to do like controlled microstructure where you need it, et cetera, there's a lot of art involved in terms of how you roster. Traditionally, all machines were rostered like that, row after row. If you buy a 3D printing machine, that's what you're going to roster. But you could roster, if you want to control the microstructure field, you'll find that you're rostering right here, you're moving there, you're moving there, you're moving there. So the rostering scheme, if you're using lasers or electron beams, so it would be way, way different, right? So to come up with controlling the microstructure, it takes a lot of that, knowledge and know-how. Now, a couple of examples. This is actually right here is the Shelby car. Okay, and what we did in about 4 years ago, we printed the car in, I'm going to say, a few days. 3D printing of the body of the car. President Obama came and cut the ribbon on that car. It's a Shelby Cobra car, okay, sport car. Everything is, the body of the car is 3D printed, okay? So when you do a lot of 3D printing of large parts, you're gonna have a lot of issues with composites. Because of thermal profiles and things like that, you're gonna have cracks, things rip and so on. So you have to understand, residual stresses and delamination and so on. So, but then you have to understand, if you want to do residual stresses, delamination, you need to understand, kind of the fundamentals, but also constraints and the effect of constraints on residual stresses and delamination. At any rate, the Cobra was printed in a few days and been very successful and still is alive. It goes to places. If you take this excavator, the boom on the excavator was actually 3D printed. The top one, it's a polymer. Second one is a steel. And the beauty about it, you can print it and you can actually put hoses and things like that. When you print a large metal and you're trying to get the tolerances absolutely accurately, that's pretty difficult because you're going to get distortions, right? So how do you control, as you 3D printing, how do you control distortions? Again, this is really where you converge with models, data, and so on. And once you actually understand how to do that, then it's easy to repeat it, okay? But that actually was done live at the Con Expo in Vegas on the show floor, right? And after it's done printing, people mounted on the excavator, took it outside, and they were digging with it, okay? So these are the moon shots, so establish moon shots like that, okay? And then you try to do it, pull all of your capabilities together. Your material development capabilities, you have to figure out, how am I going to deposit this material, your modeling capabilities, your data, and artificial intelligence capabilities, and your system capabilities. Okay, so as I said earlier, our goal is really to create that, digital manufacturing. In the future, to create a digital manufacturing, we need to look at the cyber physical systems, cyber security. And also, in factories, you need to look at digital communication. You may actually be doing working on one part in multiple machines, and so you have to carry the history from one machine to the other, etc. So in our views, okay, that's really what it takes to do a digital manufacturing. You gotta have digital code, data analytics, you need to think about the quality control, you know, how you predict anomalies and things of that nature. You want to be able to visualize the data and augmented intelligence. We actually believe a lot in cloud computing, you know, for these applications and the Internet of Things in your factory of the future. Then, you know, clearly when you think about all of this stuff, you know, let's say take a chair like this, okay, you know, you want to print it. So you have a CAD drawing of it. How do you slice it, you know, to give to your printer and things like that. So these are some of the software tools that we work on. We work on the, you know, the design tools, the slicing tools, and then how you feed them to your machines. And then again, sensors. You have to embed sensors. If you're going to do anything, you have to have data. You have to embed the sensors into your machines, and that's something we actively do. So these are the capabilities in our views that are needed for a digital thread or, you know, digital manufacturing. You know, we talk, the digital platform is really good for qualification and certification. You don't qualify or certify the part. You qualify and certify the process. So, as I said, you know, for the nuclear reactor, you know, that's what we're trying to do. It will be a 4 megawatt reactor. We started a year ago, the idea to deliver the reactor in a total of 4 years. So we have 2.5 years to go. Okay. So we have to understand, you know, defects. If you're trying to actually certify a reactor today, you know, you have to go to the USNRC. It takes a long, long time. Okay. What we're trying to do is to take this reactor and test it on the campus of our lab, and that's the reason it's full. It's a safe fail system. If you go above 6 megawatt, you have to go through licensing process and things like that. Okay. So you do the planning, you do the modeling, you monitor as you print, and then you characterize, and this is not an open loop, and you go back and forth. Okay. So that's the kind of stuff we're trying to do as far as creating a digital platform to be able to qualify the process. These are some of the systems that we have. So the big area additive manufacturing for polymers, it's an 8 foot by 20 foot by 6 foot build. Today you can actually put down about 100 pounds per hour. When we started on it, you couldn't do that. You couldn't put actually a pound per hour, right? So the extruder on this is actually preventing overage. Okay. And that's the reason you're able to do that. But again, when you put lots of materials, there's issues, okay? Delamination, residual stresses, so you have to figure out how to manage it. Magnum Venus product system is actually a thermoset material. So again, it's a reactive system. And so we work a lot on the material development associated with 3D printing. Because some of the materials don't exist for 3D printing. Okay, so if you look at, some of these systems, like toward the future metal additive system, a lot of them is existing materials that are really not suitable for 3D printing, so you have to invent these materials, right? And in composites, right there, you know, we actually have a carbon fiber technology facility. We can chop the fiber, right? You can actually take precursors, textile precursors, and we can go through certain thermomechanical treatment, okay, generate carbon fibers. We chop them and then we compound them with polymers and pellets. And that's what you use to print. So you have to innovate to create these materials. Right? So it's not just really using existing systems. And I would say like GKN, it's an aerospace company. They're interested in titanium. And you know, we work with them on that, on the aspects of the material, but aspects of the in-situ process monitoring and so on. But these are some of the systems that we have. The one over there at the end on the top is actually, we call it the Skybam. It's printing concrete. And like sky cameras, Skybam, you don't really, the If you want to print, say, something like this, you need a machine bigger than that. If I'm going to print a house, I can't get a machine bigger than a house, right? Right. So the idea here is you got the head of your printing, okay, is really hung off of pulleys and ropes, right? And then you feed it with the natural material concrete. And again, you have to work a lot on the viscosity of the concrete, how the concrete sets, and all of that stuff, okay? So these are, the slump ratio of your concrete, all of these are important things. But what we're trying to do is, this is, when it comes to controls, it's a pretty tough a problem because you have to have a great stability right there, right, of the head. And so you have to figure that out. So we're building systems like that, okay, where it's not a traditional machine, it's different, okay, for printing, for sustainability and things of that nature. Just to quickly, I mentioned, materials. There is an example here where you actually, if you go to the state of Maine, Maine got a lot of forest products, and the forest product industry over the years disappeared out of Maine. Right? And so if you can take wood chips and you go through a lot of actually, I'm going to say, dewatering, drying processes, and so on, you can actually make nanocellulosic fibers. And these nanocellulosic fibers have roughly about 7 times the strength of steel and as stiff as Kevlar. If you compound them with, say, polymers, maybe bio-based polymers or polymers, you can take them and print all kinds of things with them, right? So what we're focusing on is actually trying to deal with the process itself. The process is really energy intensive and water intensive process, right? But that's a big challenge, right? And then what we're able to do is to print things like this. Actually, I forgot that November or December, we printed a 27-foot boat with the University of Maine using nanocellulosic materials, and both of their senators got into the boat in the water. So they're good risk takers, okay? But that's one area that we're focusing on, okay? But you can think about it for other areas of biomaterials. I think in this case you should think also about recycling, right? Okay, how can I make these, whatever I'm going to compound with it should be recycled, okay? If I'm going to take in nanocellulosic materials, okay, green materials, I'm going to print something with them, I should actually make sure the entire cycle is closed. And that takes me to this slide. I think, in general, the circular economy is an important concept. And I think it's going to be an important concept for the future. Right? When we talk about water, some of you are interested in water. If you look at our water systems, the way they got designed, it's linear systems. Okay. So again, how do you make our water systems closed, in terms of reuse and things like that? But I think it goes to all kind of products that we use. If we want to conserve resources, we need to think about the circular economy, broadly speaking. So in this case, and this is just an example, if you printed, composites, or you did something actively manufactured parts, how would you recover the fibers, and what would you do with the plastic and things like that? So that's what we're trying to do here, is to look at materials. There's the fibers, carbon fibers are pretty expensive. It's like $6 a pound or something like that. So you want to be able to recover them. And then what do you do with the plastic? You can convert it to other sources of energy. If you're dealing with thermal sets, if you're dealing with thermoplastics, I think you have a different game to deal with. It's much easier. Again, like things like bottles, Coke bottles and whatnot. Okay, you can recycle these. They're thermoplastic materials. You can actually take the wood chips out of whatever Home Depot does. Okay, combine the two, and here you go. You can actually print with it and all of that. Now, but in general, you want to start with something with the premise, I'm going to be able to recycle the whole thing. Having just halfway may not be acceptable in the future. So that's something we're working on in the manufacturing demonstration facility, is the circular economy. Now I'm going to switch gears. I'm going to talk about large-scale environmental experiments that we at Oak Ridge been involved in. These are in the past, and I'm going to actually emphasize these right here. Okay. So before I say that, all of us work on, Earth system models. And the idea is really to focus on decadal predictions and be able to get accurate predictions, what happens with, the climate. Right. But there's a lot of uncertainties associated with the models, a lot of the processes we don't fully understand. Right. And so this experiment, Spruce, that we have, it's in the peatland, it's in Duluth, Minnesota. It's mainly focused on two things, elevated CO2 and the effect of elevated CO2 on plants and the soil and also warming. So we have actually these chambers, and in the chambers you can elevate CO2 or you can elevate temperature or a combination of both. And we're trying to focus on understanding what happens to the plants and the soils and the microbial communities in the soils, right? And how they signal to plants and things like that, simulating various aspects of that. So that's one of the field experiments that we have. These experiments will inform models and things like that. This is another experiment that we have. I'm going to actually, it's not, I'm going to talk about the NG Arctic. Okay, so we have a big environmental experiment, next generation environmental experiment in the Arctic, and we contribute to another one in the tropics. Okay, so in the Arctic, the question of the thawing of the permafrost. Okay, how it thaws, in the dry conditions, wet conditions, what do you get released? Methane, CO2, etc. What happens to the soil, to the microbial communities, to the root of the plants, and all of that. So trying to focus on that in this experiment. Again, the idea is to be able to feed this into the models. And if you look at the Earth system models, they have also sets of models. They're nested models, okay? But one of the aspects deals with the subsurface and things like that. Okay? So these experiments contribute to that. Again, this is the Spruce experiment. It's been running for quite some time. And we have participants from universities across the United States in these experiments. I think there are NSF PIs that participate in the experiments. And again, this is the NG Arctic. Again, it's in Alaska, a lot of focus over there, and various aspects of the experiment. Okay. This is actually two more slides, and I will end. The other thing is, so we talk about, microorganisms in the soils and what happens in, say, in the droughts, if you want to fixate nitrogen in a carbon cycle and things like that. Unfortunately, to identify the trait, the phenotype of a gene, it takes a graduate student at a time. For example, at Oak Ridge, we focused for some time on the whole question of mercury and the methylation and demethylation of mercury. And it took multiple years to identify the two genes that are responsible for that. And it was an open question for over 40 years. So the question really, how can I rapidly identify the functions of genes? And how, genes manifest themselves into the ecosystem. So we don't really know the properties from one biological hierarchy and how it dictates itself at different scales. So what we're trying to understand, what happens if something happens to a certain gene, what it does at, say, an ecosystem. For example, in the lakes here, you have algae blooms, okay? So it's because of, nitrogen, subsurfaces, or actually just, let's say, water flowing down into the lakes, right? And you're moving fertilizers into the lake. So the question is, how do you fixate nitrogen? What's the role of organisms and plants in fixating nitrogen? So we're trying to understand that. To do that, what we actually working on at the lab is actually a facility concept to provide 100-fold rate of identifying the functions of genes. And to do that, we identified multiple cores from lower scale where you look at protein synthesis, you characterize them, molecular networks, genetic manipulation, etc. But it's at the molecule and cell level, and then you go to the synthetic biomes, and so in defined environments, you're looking at microbial communities, synthetic microbial communities, plant microbe system, and things like that. And then it's really, when you try to understand how organisms behave, you need to understand how they behave in their natural environment. Okay, because they signal differently depending on the environment around you. So to try to look at them in defined host and natural systems, one of the things we've done, we created a gene-wide association study for popular, one of the plants, and so we understand, how to manipulate pathways in popular to produce more lignin, less lignin, more cellulose, hemicellulose, and so on. So that's really another area that needs to look at. And as you see, you need to have the analytical tools and the computational tools. And I would argue this kind of thinking is what I tried to show earlier in the manufacturing space. You have certain things, but you got your characterization and around that, your computational platform. And so you have all of these, need to work together. So you could see in a very applied sense what the MDF was trying to do. This is what we call the bioscale facility. You could do with it, things like extreme events. How do plants respond in a drought, right? And how can we actually make them more drought tolerant? Okay, this is one way to trying to figure out what are the genes responsible for what. Okay, and you're trying to, really engineer the genes and so on. Biosecurity in general is an important topic, important to agriculture, to plants, to humans. In national labs, we don't focus on humans, we focus on plants and agricultural type things. And mercury, I mentioned the example, but mercury is a problem, it's an international problem. Wherever you do mining, there's mercury. It's everywhere. So how do we deal with the whole methylation, demethylation of mercury? Carbon cycle and nitrogen cycle, I think, really also important. And biofuels, there's all kinds of plants, if you can, manipulate them, deal with them, that would be great. As we start to face more problems in climate change, okay, if you go to desert countries, there's certain grasses are actually, if you go to Arizona, I forgot what the name of the grass, but it's actually in the Arizona desert, and it can catch on fire. And you can have wildfires in the desert, okay? Things that people don't really think will happen, but that's what's happening. And in many other areas, you get dust kicking and so on. Can you grow something that will be a cover in the desert and so on? Again, these are the topics that you could address with these are not my areas, okay, expertise, but I gave you just a general perspective. And Hamid said, talk about environment. So I try to talk about environment, but glad to answer questions.
Thank you. Any other questions before we do the questions? At this point, open up for appreciation. We're going to do this. This is going to look very similar to you as the Winter Distinguished Lecture Series. And when we came up for this walk back to the Winter Distinguished Lecture Series on our fridge, was that for you laureates, so the question was, can they put this on their desk?
I will.
We're going to do the same.
I will.
Right? And so with that, did you take some questions?
I should.
So let me ask the first one. Could you talk about some of the fundamental questions you think need to be addressed in the manufacturing space to make, what are the top few questions right now that need to come in from the fundamental side to make additive manufacturing and techniques like that, realistic from an economic cost perspective?
Sure. I think what I presented in a lot of ways is really a big area additive manufacturing. Right? So So the big question is still in the big area of additive manufacturing is really the qualification question. I print a part, how do I ensure that part is actually qualified? I.e. free of defects, or if there is defects, we understand, they're embedded defects, not surface defects, etc. So I think that's still really,
So defects.
I think the other thing is if you look at, functional materials, you're trying to print functional materials, including batteries and so on. I would say, engineering interfaces, because again, when we talk about, functionally active devices and so on, the interfaces is everything, right? How do you actually, additive manufacturing, you can actually manipulate the interfaces. Like for example, if you want in a certain electrochemical device, you want to have triple point boundaries, and you want to manage the density of the triple point boundaries with certain, say, chemical characteristics of grain size. How do you do that? Okay, so to me, you really need to go to, I'm going to say depositing an atom at a time. So from atom at a time at the interfaces to big area, that transition would actually be needed. But I would say if you look at, say, like egg-shaped memory alloys, if you want to do that, is manufacturing. Same question.
Other questions?
Very nice talk, I'm impressed. For the carbon fiber, so what's exactly the cost now per pound? It's $10 per pound or $6 per pound?
It's $6
$6
per pound. Okay.
So
And what we did, so it depends if you look at aerospace quality carbon fiber.
Right.
Okay. Aerospace is quite expensive.
Right.
What we've been able to do is to take textile precursors, right? Okay, and you can actually, oxidize them and carbonize them and so on. You can get strength and modulus suitable for automotive applications, right? And then once you got that, you can actually, whatever form factor you want to do with them, you can. Lately, we've been trying to drive the cost down.
Right.
I'm actually a pretty strong believer that we should not gasify coal.
Mm-hmm.
Okay. So what we've been working on is taking coal pitch, right, and converting coal pitch to carbon fiber. And that's what we've been trying to do. And that's been successful in the lab. The questions of scaling yet to be answered. But that's, so you need to drive it down. If you want carbon fiber to be, widely used, you need to drive the cost down. But I would argue the following, okay? I believe carbon fiber is going to see way more utilization than we think, and the reason is because the emergence of electrification. Okay? Electrification is, I really believe it's a hockey stick, right?
Right.
So if you're going to electrify, you're not going to carry a lot of mass. So you need lighter weight vehicles and so on and so forth.
Right.
And carbon fiber is the material. And you see it today, there's people, a few years ago, 10 years ago, nobody wanted to touch composites because of repair and so on and so forth.
Yeah.
That's changing.
So what's the thermoplastics you use for carbon fiber? Make composites?
What are they?
Yeah, polycarbonates or what's?
No, I don't know exactly but it's not that.
Okay.
Polycarbonates, you use them, well, I don't know. Okay, the exact chemistry. Yes, please.
So, I noticed, interesting. So I noticed you do 3D printing at a very massive scale, so huge extruder pads, high performance. When the material goes through the transition from liquid form to solid form, when it sets, how do you drive away the heat? Because I know it's a problem, because the material becomes insulated by itself, and the inner part, it's a problem to drive away heat from this one. So how do you drive it?
So if you're trying to, first of all, I take the question like that, okay, we're trying to manage the roster profile, right? So I got heat, I'm not trying to actively manage the heat, okay? Otherwise, that would add cost to the process. But I'm not trying to deposit more heat unless I need it, right? And so you can actually, when I talk about porosity, machines today, you buy a roster like that. In our case, when we roster, I don't melt some of the materials to the melting point. I heat them up to some level and I move on. So we do a lot of computations such that I can heat to certain levels, okay, and so on and so forth, to manage thermal, but also to manage grain size and so on. Okay. It depends on what you want to do, right? Okay, you could actively cool your systems and so on with low air or something like that, but we don't do that. Okay. So you try to manage it by really, as I said, modeling and simulation, understand before you go on, this is what I'm going to be able to do by rostering profiles to control how much heat you deposit. So normally, like when you look at it, if you think about it, your thermal profile controls, in a big way, your grain size. Okay, and the history will control, the shape, et cetera, et cetera. So we don't do active movements or room temperature stuff and so on.
Other questions? Go ahead.
Yeah, thank you very much. Basically, thanks for the talk. We are very interested in applying the additive manufacturing for biomedical applications. We actually biomedical. So we actually have some initiatives here for combining composites and some of the like antibiotic materials together, nanoparticle or agent together for say antibacterial or antivirus type of devices. But we feel like more often than not, the experimental part efforts is more random, like we try different things. So could you actually shed some light on the potential role AI could possibly play in developing or optimizing this kind of?
To me, one can look at say, okay, I have a multi-objective optimization problem, right? And this, one way is the shape. Okay, I'm going to optimize the shape. The other, I want to optimize the properties, the mechanical properties, maybe grain size. In biomedical, you have to worry about texture, like surface properties and things like that. And so, what we are trying to do is really to, in the lab, in the manufacturing demonstration facility, do a lot of tests to create a lot of data, do a lot of characterization. And then once you have the data, you change all the process parameters, you create certain things, you change the process parameters. And then, using high performance computing, to help us in actually, like, if you think about like a giant lookup table trying to fill certain parts of the giant lookup table, right? And then you can use, convolution neural net, et cetera, whatever the flavor, to trying to decide on if I'm interested in A, B, and C properties, what is the processing path to get me there? When I talk about the rostering thing that we try to do, and we do it in a little bit, different than the traditional stuff, is to give us the right microstructure, etc. Where did that come from? Through AI. So I see actually, the truth, I see AI, and I don't mean it in a commercial sense, okay, right? Just machine learning in general with big data should inform us a lot about how we need to process. The trick really is in understanding what you need and what would be the processing parameters, your process, how you control your process, give you what you want. That is the role of, traditional computing and artificial intelligence. And that's the way you have to have data, right? If you don't have enough data, you will not be able to do it. Either you create it in a synthetic fashion or experimentally.
Hi, thank you for coming in. Nice talk. I actually had a question based off that. What kind of data do you find the most helpful at this point and moving forward, analytics-wise? What do you look into the most? Yeah.
So okay, although I'm gonna extrapolate because I'm not the one who's doing the stuff. Okay. Right. But I truly believe your time-dependent thermal measurements or thermal profiles in additive manufacturing, especially metal additive manufacturing, is really critical. And then you to look at the same time at your solidification region, right? Okay, what's happening, right? And so we do a lot of thermal profiles, kind of wide area thermal profiles and point measurements. And that's to me what's really critical to help you understand, right? in this case.
Yes.
Any other questions? If not, let's thank Will once again.